So, allow me to continue where I tried to leave things. Some samples I could not collect, just now I got the samples. Please have a look at this, which is taken from the famous Pentium cooler. So, typically what you see outside is this, including that Intel's name, probably it is from an OEM, because I do not think Intel will be wasting their energy in making these things. What is however very important is that the whole module has been made like this. Right now I can't see inside whether it is actually a copper core or anything, the whole thing has been welded, soldered and welded inside, so they cannot see anything. However, if we do break it open, chances are it has a high conductivity copper core inside. The advantage of it is to make this heat sink effective, that is there is the thing about fin effectiveness of the heat sink. Two things have been done here. One of them you will notice is that by conductivity, this conductivity from anywhere here to this should be maximum, otherwise chances are there will be already a drop. Hence the highest possible what do you call special type of copper alloy has been used here. I am not very clear as to why this small step has been given. It may be part of some way of equalizing the what do you call the heat to this thing. In some of them the core is made up to here and afterwards a small bore is drilled here. I have not been able to figure out, maybe you should contact those people. And another very interesting thing is, you see these fins have a very peculiar, first of all they are radial. If you are to make it radial, chances are you still have some issues about this has to be thick at the base, and as it comes out it should become thinner like that, but it will beat the whole thing because you will end up with a what you call a sun type of this thing, where while the base is here and there will be too much gap here which we cannot do anything about. So, what they have done is, as a wire media it starts thin, narrow, and it goes a little thicker and then it splits again, so that at the periphery we still have, at the periphery we still have lots of fins which approximately correspond to the fan that has to sit on top of it. So, we have this fan which sits on top of it, and you see here that center area where the air does not go, this fan directly covers all these areas, and the moment this fan starts turning, two or three you will notice is one part of it is probably axial, but then while it exits, exit is, while this is axial, exit is radial like this, and when the fan rotates there is a always one what you call flow is not straight, and to make more contact area between the sides of the fin and this, it has also been given a small forward curve about it. This is only my interpretation, maybe somewhere in the open you probably will have the data in it. I just wanted to point out that these tricks are whatever it is, somebody has to come out with the concept, and later on you can work out with the CFD or your simulation and all that and work back. Unless the quantities are large, the OEMs also will not be able to help you about it. This is regarding the heat sinks which I wanted to show you earlier, and I managed to get it. Now, second thing is, let me get back. If you see the morning, I left you here because my module did not run well. Have a look at it again. This is part of the bioassay assembly. So, we have some special cups, and from various reasons we do not want them to be shaken up or stirred. If you stir it, we have a small problem. So, there is a what you call, there is a ferrous material, there is a magnet there, slowly it rises in. Now, it will index into a position where it is gently lowered onto the micro balance which is attached here. What I would like to bring to your notice is that when we made this item, we also wanted to have a provision by which we can cool it or heat it as we like. So, in another dummy slot at the back, we can have a small well which will it can be heated or cooled, and then we can rotate it. The whole carousel can be probably kept in an incubator, brought out, and we can what you call attach those things here. So, you will see that now why it has been made is maximum amount of care is being taken such that you do not stir it, and the bottom of it is open. There could be the medium liquid inside which may spill on this, and similarly when you want to place it on one of those positions, the device should remember where it has taken it from and come back again to the same position. And when we make a drive for the stepper motor what you call system and all inside, the whole base is available for us. You see, I have a base here, I have a base here. Directly things can be mounted here, and next point is that heat should not disturb any of our measurements, and you see very gently it is being placed there to prevent any what you call wrong this thing about the balance, because this balance has a 3-digit precision. So, we want to see whether the rate of growth of the germinating seeds are under our control at a given temperature and what you call ambient conditions, because most seeds they see a rate of temperature rise also which is critical. Lot of the root activity and the germination activity is just at the surface. So, these are all, I have no clue about what it is. Now, we come to one more demonstration, this time by the manufacturer. He will explain to you, have a look at it, a simple demonstration box.
Hi everyone, my name is Dan Rice. I'm a lead engineer in the Strategic Product Development Group here at Advanced Cooling Technologies. And today we're going to talk about heat pipes and their thermal conductivity values. So we have a demonstration to show you. Here we have a copper water heat pipe, and here we have a solid copper rod. And we're going to be inserting them into our demo box, which has a hot well and a cold well. And we're going to be looking at the difference in thermal conductivity between a copper rod and a copper water heat pipe. So the first thing I'm going to show you is we put the copper rod into the heated well. We're actually going to be able to see the temperature change as the heat conducts up the rod, because there's a color changing paint on the outside of the surface of that rod. So it's a little difficult to see here, but the paint is turning from green to yellow slowly, and so what we're actually witnessing is the heat conduct up that rod. So I'm going to let it progress a little further just so you can get a feel for the rate that it moves. Copper has a thermal conductivity of about 380 watts per meter Kelvin. So it's a good conductor as far as solid materials go, but in a minute here you'll see how much better the heat pipe is. So okay, so you can see the color change, and it's slowly making its way up. In another couple minutes it'll turn.
See that rod which is being inserted, the red one is a hot well, meaning at the bottom he probably has some oil or some other liquid. That other blue one is a cold well, and then the test specimens have been coated with a color changing paint. Usually most LCD materials they will have exhibit that properties. So, depending on the length of it and depending on the rate of heating, the color changes continuously. I try to point out the same thing to you, saying in your old physics class there used to be a container, and then there used to be 2 or 3 of them, two high conductivity, one is a low conductivity, another is an insulator. The whole thing is coated in wax, and then you have small sliders, you put hot water inside. The highly conductive rod, it takes heat to the bottom quickly. So, there is a small slider with where the wax melts and comes down. Medium conductivity, it just starts and leaves, and the non-conductor does not allow the wax to melt at all. Now, in the modern this thing now, if you see here, instead we now have a color changing paint. So, what he has done is he has put this one solid rod directly in the hot well. Next he is going to put the heat pipe into the other well. So, you watch here.
Completely yellow. But now I'm going to put the copper water heat pipe in, and you'll see that the color changes almost instantaneously. So it's already.
You have seen the whole color has quickly changed compared to this. I will try to play it back a little and we will see how it starts here. Watch.
The heat pipe is. So okay, so you can see the color change and it's slowly making its way up. In another couple minutes it turns completely yellow. But now I'm going to put the copper water heat pipe in, and you'll see that the color changes almost instantaneously. So it's already essentially the same temperature at the top as at the bottom of the heater block. And so that really demonstrates that high effective thermal conductivity that you get when you use a heat pipe for cooling electronics or other devices. So at the same time we can move from the hot well and insert it into the cold well, and you're going to see that temperature very quickly go to the cold temperature and return back to green. If we do the same thing with our solid copper rod, that process takes 1 to 2 minutes. So this is just kind of a really practical example of the difference in effective thermal conductivity between a heat pipe, which is a thermal superconductor, and even your best solid metal conducting materials like solid copper. So that's all for now. Thanks.
Well, I expect that it is about as clear as possible. Now, while that is from a commercial source, I want you to watch. We have nearer at home.
The flow through the tube would be in the low Reynolds number zone. Secondly, if you think of the
This is a full 1 hour lecture by Professor Dasgupta. I suggest you, what do you call, you take time and read it on your own.
This is the region which is not participating in heat transfer. So problem where access is heat source near this higher temperature pipes and so on. The first thing that one should concentrate is it's very low thermal conductivity, very high. So towards the intermolecular force gradients, micro heat pipe only, where you would let the liquid undergo a change in the radius of curvature. The diameters are between 10 to 500 micron, and the length could be a few centimeters. And the flow inside the heat pipe is caused by a change in the radius of curvature. In fact, a change in pressure caused either by a change in curvature or by an intermolecular. Okay, I couldn't write properly, but these two are connected. One has to, even the vapor is going to start to return, likely one would encounter, but we haven't one, because the temperature of the liquid many gradients to drive and which are slowly coming.
See, the most important thing you need to notice is this is a wickless non-circular channel. There is no wick, and because of the various very narrow sizes, the change in pressure due to changes in capillary and intermolecular force field along length of the heat pipe seems to aid in the flow. I have not found it anywhere else, and I am very much obliged to this lecture, module 11, lecture 11 on micro heat pipes. I suggest you go through it, because this takes 1 full hour for you, and tremendous amount of analysis and how the forces change, all that has been given. You have seen that, no? There is something about the meniscus, surface tension, wettability, solid liquid interactions govern the behavior of the various interfaces, liquid vapor interface. The fluid flow in the evaporating meniscus results from a change in the meniscus profile. This is where probably the new, what do you call, nano science has come about. So, while I belong to the old school, I am not yet here. So, it is for you to, I suggest no, please follow it. I am not an, what do you call, this is at one point how the liquid looks, and other point how it, this thing, how the transition takes place along the length. So, that has been given here. I suggest you follow this, and I am sure tremendous amount of analysis has been done saying liquid pressure as a function of the radius of curvature from Young-Laplace equation and all these things have been derived. To be honest, I have not used it, and as such no, I cannot what do you call, comment on it, but I suggest you need to check on this for triangular and for rectangular. They have done you know, tremendous of an analysis in this, and then there is a follow up lecture also on this. Okay. There is a
So in today's class, what we are going to do is to recapitulate on what we have covered in the last class, and then think about the components of pressure. Liquid vapor interface is comparable to the reciprocal.
okay. You please read the whole thing.
So this principle
A small part of it is repeated because for people to understand, and then this thing no, saying surface roughness may play a dominant role and all that, and in the conclusions it is a matter of time that these will eventually be available wherever we want those things. I just wanted to point this out and then take leave at this point, and then we will try to get back to more practical this thing, especially what a vapor chamber is. So, in the next meeting I will come back and talk a little more about, there are small vapor chambers which do not have a wick, it is a little like boiling water in a closed container. So, at the bottom the what you call the phase change you know, mechanism will allow boiling, and then directly on top it gets cooled, and along the lines or inside the thing itself no, by forming the moisture condenses and continuously things take place. So, that is typically a simple vapor chamber. You have a small, what you call, small container filled with a liquid, and then continuously things change in it, and again a little bit of theory, a little bit of experiment, and finally you have commercial devices available which are directly fixed between the chip surface and between the heat sink, because we need a very big what do you call, very low degrees centigrade per watt. The thermal resistance has to be low, and there you cannot afford to have huge volumes like this. It is expensive, it is what do you call, heavy and of doubtful you know, this thing cost effectiveness, but in a case like this we have no choice, it is a must. So, thank you. I will stop here. I did not want to play the full video. I kindly go to the back to the NPTEL channel, look for this micro heat pipes from IIT Kharagpur, and beautiful treatment has been done here. And coming back, if you still are interested, that stuff about the myths about heat pipes are also given here. I will just search the same company talks about same this thermalloy Avid. What I have spoken or what is taken from their main website, this lady will explain, you have a look at it, mostly saying how this is as good as the other.
Has decades of experience with designing and manufacturing heat pipes and heat pipe assemblies. Heat pipes are the best way to transfer heat, spread heat, or increase heat sink bit efficiency. Here is a custom Avid heat pipe assembly. This assembly can dissipate up to 150 watts. Heat pipe assemblies have 3 zones that contribute to their heat transferability. The first zone of the heat pipe, the evaporator, is where the heat absorbed from the device evaporates local liquid into a vapor. This vapor travels through the second area, the adiabatic cavity of the heat pipe, into the third zone, the condenser, which is the cooler region of the heat pipe. Here the vapor cools and condenses back into a liquid. Through capillary action, the liquid then returns to the evaporator region of the pipe, and then the cycle repeats. Because of the latent heat of vaporization, water can absorb and carry more energy or heat during phase change from liquid to vapor. This makes it so much more conductive than the metals typically used for heat sinks. Unfortunately, although heat pipes have been used since the 1960s, they are a commonly misunderstood technology. Replacing heavier and more expensive almost double the size of this one here. Myth: heat pipes are heavy. Truth: although most you would need a new and heat pipes can drastically reduce the and replacing heavier and more expensive materials. For example, replacing a copper base. Here's a solution from earlier that can dissipate up to this one here. Myth: heat pipes are heavy. Truth: although most often made of copper, they are hollow. They can actually decrease the weight of your solution by improving thermals in a variety of ways. Myth: if they break, they will get liquid on my electronics. Truth: heat pipes are one of the most reliable two-phase liquid cooling solutions, and rarely if ever break. If one did, the minuscule amount of liquid
So that is a pipe cutter, the tube cutter, she is trying to make a dent and open the heat pipe.
here, I'm going to open up the heat pipe and we're going to drip out some of the liquid that we find inside. This is going to take a few moments, so bear with me.
Looking at all the pictures we have seen so far, you see already it is split in two and then there is a beaker ready. So what happened to the liquid? We do not see any liquid anywhere, nothing, no liquid. So all the liquid is already in the,
Nothing's dripping out.
it is directly absorbed in the wick. So you are not likely to have any liquid leaking.
Myth: heat pipes only work with the evaporator and condenser on the ends. Truth: heat pipes work along the entire length of the heat pipe. Heat pipes will consistently move wherever it is hot to where it is cooler. Because of this, they are often used for spreading heat and not just transferring it. Here are examples of heat pipes being used as spreaders in the base. And here are solutions where the evaporator is in the middle. Myth: heat pipes cannot be used in freezing conditions. Truth: this is false in 2 ways. How a heat pipe operates in given ambient conditions is dependent on materials. Most commercial applications use copper and water. Other materials and fluids can be utilized depending on highly specialized requirements, allowing heat pipes to work in even the most rugged conditions. Secondly, even with copper and water, the solution can be designed to mitigate environmental conditions, such as starting in a cold environment. I hope you found this video informative. If you have more questions on heat pipes and their applications, contact Avid. You can also order one of our heat pipe kits. Heat pipe kits are tools to enable our customers to explore, test, and build with heat pipes in their own labs and experience prototyping your own heat pipe cooling solutions.
So search for yourself. Long ago we could go to a library and then look up various things. Right now technology now permits us to search for it directly online. The only what you call caution here is something like the perpetuum mobile, something like the what you call get power by this and all that, they are all fake and fraudulent thing. They are all made maybe like a gag. But the reality is, if you actually go to serious lecturers anywhere in the world, including some manufacturers, they give you a lot of information directly. Now, the second point is it worth for you to trying out? Let us say you are a curious person. Yes, there again one more time there are ways of making a heat pipe and so on, and if you go back again to the YouTube channel, you will probably find how to attempt to make your own heat pipe. Same thing it is with Peltier. Peltier modules are available, you can in fact order them online and then try to build your own systems as you like. So, I will take leave of you now at this point. So, thank you.